All right. Okay, welcome to the afternoon session. So our first speaker is remote. Annika Peter she's a professor at Ohio State, and she'll teach us about how to calculate dark matter distributions, I guess. So you want to run a simulation is an awesome title. All right, so Annika, please go ahead.
Hi, everyone. How are you today? Good. All right. Well, I can see that there are a bunch of people in the lecture hall, lots of people online. Can't really see individual faces so much. So for those of you who are online, feel free to use the raise hand function. And I trust that for those who are at Les Ouches at the physical location, you'll interrupt me when you have questions. All right, so the goal of the next couple of lectures is to teach you a little bit about simulations, a little bit how to run them, and a little bit how to use them. It's a huge topic that I can't cover in a lot of depth. So this is meant mostly as a way to sort of plant some seeds of ideas in your brain. And in the Google Drive that I've provided you all, there's an extensive reading list that I will probably add on to at some point. If you think there's something missing from the list and want it added, please email me with the reference and I can add it to the list. But this is really meant to be the beginning of a journey for you, not the end. And in the discussion or exercise section later this week, I'll have a few ideas for things that you could try out yourself. So the best way to learn something is by doing. And so if this seems interesting to you, something like you might want to pursue in some fashion, the best way to learn how to do it is to do it. Okay, so I just want to point a few things on my title slide. So first is my group semi-regularly runs social media accounts on Instagram and Twitter. Honestly, Twitter has been a little more active, although still not as active as it once was. But if you want to see sort of what my group does and things that we post about, you can check us out at How We Science on Twitter and Instagram. The other thing I want to point out is this beautiful graphic, which doesn't actually come from my group. It comes from the Aug3 project. And I'll talk a bit about Aug3 later, but it's one of these large simulations that has dark matter and hydrodynamic treatment of galaxies. And it's sort of what I call this like Sloan digital sky survey of the simulation world. It's got a ton of public products in big boxes, and you can just, it's a nice playground if you have a science question that you want to answer with simulations. All right, so let's get going for today. All right, so just a few words on what's in the drive and how to use these notes. So these PowerPoint slides will be posted or are already posted. If you look at the little comments or notes section at the bottom of each PowerPoint slide, many of them have some extra references and sources in them. But the bulk, as I mentioned before, of the references related to this talk are in a document that lives on Google Drives. I think right now the reference list is about 7 pages long, and it's probably only going to grow. Oh, Elizabeth, I'm teaching a class right now. Dad's downstairs. Okay, sorry, my son just got up. All right, so if you're interested in any of these topics, I've sort of grouped reference by topic, and so you can just check those out. And then later today, I'll be adding exercises to the exercise directory. All right, so this is sort of the theme of this lecture. So How many of you are cosmology enthusiasts in the audience? You just raise your hand. Okay. So for how many of you, how much of your cosmology experience has been basically using the front end of Dodelson and doing sort of like linear perturbation theory cosmology? Okay, fair number of you. All right, so the theme of this lecture notes is that there are times when linear theory cosmology is just not going to cut it. And if you want to understand cosmological evolution, you gotta put it on a computer. So, so this picture right here is of one of the supercomputers at the Ohio Supercomputer Center. It's the Pitzer machine, and that's the machine that my research unit, the Center for Cosmology and Astroparticle Physics, owns a part of. Okay. All right, so when do you want to go to a computer? When is cosmological perturbation theory just like not going to cut it, or analytic methods? So one is when your system is nonlinear, and we're going to talk a little bit about what that means. Another is when your system is chaotic. And then finally is just when perturbation theory breaks down. And these are kind of coupled in cosmology. Systems going nonlinear and perturbation theory breaking down are related to each other. And we'll talk about chaos in a bit too. Okay, so I'm going to stop these slides and go to a video. So we're going to talk about what it means for things to go nonlinear, at least in a cosmic context. So I'm going to stop sharing the screen and then share a different screen. Just a sec. Okay, so in this case, I am, can you see something that looks like a spider web on my screen? Okay, great. All right, so I'm going to show you a video of basically the formation of a cluster. So it's going to start already when the system is already a bit nonlinear, but what we're going to see here is the growth of structure. Okay. Oh boy. All right. I had this actually downloaded. I will share a different screen. Of course, now I have lost it. Okay. All right, so this simulation starts at redshift of 20. One thing that I will caution you about is in a lot of videos of simulations, what you see is not actually the cosmic expansion. That has sort of been divided out. And so what you're really seeing is in sort of co-moving coordinates, the growth of structure. So that's an interesting point. I love to see the expansion of the universe in videos, but you just usually don't see that. It's usually, the simulations are usually done in co-moving or represented in co-moving coordinates. That's a great question. Thanks from the chat. So the distance scale is you're going to see it pop up, but it's the box size across is something of order 200 co-moving megaparsecs. Oh yeah, now you can see it. Okay, so I'm going to just play this video. So this is just sort of 200 megaparsec on a side box going from redshift 20 till today. And so you see these little ripples of structure. You see the contrast becoming greater and greater. And you see this large structure forming in here. This is a galaxy cluster forming. All right. And so what we saw there is the universe go from fairly homogeneous and with small density perturbations to a universe today that has very significant density contrasts. All right, and one way to see sort of in a more sort of quantitative way what's going on is if you look at, this is another plot from Fokker-Springer. So the video that I showed you before was from the Millennium simulation, which was the brainchild of Fokker-Springer, who is one of the great coders and algorithm developers in the cosmological simulation world. But he also has a nice set of lecture notes, which are linked in the slides. But he has this representation of basically one of those overdensities. So if you look at one of the overdensities in the video, in sort of standard cosmological theory, if you looked at sort of the sort of size of that overdensity with time, which is represented with R of t, then in linear theory, that overdensity is just going to grow in terms of spatial scale. So that the spatial scale of the overdensity will just grow. But in non-linear evolution, what happens is that that overdensity, if you look at one shell of that overdensity, at some point, it's going to expand with the Hubble flow. But at some point, because of the gravity of the matter inside that shell is going to collapse in on itself, which is what you see here, represented in this red line, and that system is going to collapse. So this is a result from sort of cosmological theory that's been known for like over 50 years, is that if you have a matter overdensity, that eventually that overdensity will collapse in on itself and create those structures that we saw in the video, these dark matter halos, these self-gravitating blobs of dark matter that have decoupled from the Hubble flow and are now these dense, distinct blobs of dark matter. Okay, and so to study the evolution of those, you really need to go to a simulation. You're not going to get the full structure of those halos and the clustering around it just in linear theory. Okay, so the goal of many simulations, or all simulations, I should say, is to take some set of initial conditions. And for the rest of these lectures, I'm going to refer to position and momentum coordinates as Q and P. So position and momentum. So you're going to have some set of initial conditions for a set of particles, although as we're going to talk about later, sometimes it is better to represent dark matter as waves instead of particles. So take this with a grain of salt. So right here, I've represented dark matter particles or you know, nuclei and electrons and so forth, but it may not be appropriate to represent these as particles. In any case, you take some set of initial conditions for your set of particles, or you know, however you're going to represent the matter contents of your system. You're going to apply whatever forces are relevant for your set of particles. And then what you want to know is what is your system going to look like at later times. And the way we quantify that is in terms of like in the context of dark matter particles, what are the positions and momenta of those particles at a later time? Okay, so I'm going to show a bunch of ways to figure this out. And so what I'm going to do is I'm going to give you sort of a space, a way to organize how to think about starting with some initial set of initial conditions, and how to figure out how that system is evolving, I'm going to represent the things that you should be thinking about when you're trying to figure out how to do that. In sort of like, I'm going to show a 2-dimensional coordinate plane, but it's really a little more multi-dimensional than that. But I'll talk about the multi-level dimensionality as we go along. Okay, so the first consideration is, how many particles do you have? Do you have like just a few, or do you have some enormous number? So the way I like to think about it is, when you're down here near 1, actually, can you all see my cursor? Okay, great, thanks. Okay, when you're down here, every particle has a name, or what often happens for these what are called few body problems, we're often considering, for example, like, and this is not going to be a fundamental physics application, but like a typical application just in physics would be like planetary systems. So in planetary systems, every planet has a name. Even if you go to extrasolar planets, you could give each particle a name, and it's meaningful, and you care about what happens to every individual planet or star or moon in your system. On the other extreme, and we're mostly for part of today and basically all of tomorrow, we're going to talk about this limit. When you have just an enormous number of particles, and here enormous number really means something that's much greater than 10 to the 6 particles. In that case, you're not giving every particle a name. And typically in this case, we're talking about a whole bunch of indistinguishable particles. And when you're really in this huge number limit, it makes a lot more sense to talk about the phase space density of particles rather than giving each particle a name and following it through space. You really should be thinking about the system as an ensemble. Okay, so really thinking about, in this case, dn represents some number of particles that's in a space, and some chunk of phase space, some volume and configuration space, that's d3q, and some volume and momentum space, d3p, where you're looking here at the phase space density f, which is the number of particles per unit configuration space volume per momentum space volume.
We have a question here.
Sure.
And Catherine.
Hi, thanks. At what point along this number line do we stop having an analytic form for the dynamics of these systems? It's like a pretty small number of particles, right?
Yeah, so that is a great question. So let me ask, what do you mean by an analytic form?
And so I forgot to explain, I have to dial down the volume. So there's like a 1 second before you start answering. Okay, it's fine. It's just that that's what's going on. Okay.
Okay.
All right. So.
Yeah, thanks. I guess I mean like an equation that describes the dynamics of the system.
Okay, so there are always going to be equations that describe the dynamics of a system. I'm going to talk, maybe I might answer your question in a slightly different way on the next slide, or one of the next 2 slides. Can I maybe take a stab at that, and then after I've talked about that a little bit, can you maybe check in to see if I answered that question?
Of course, that sounds great. Thank you.
Okay. All right. And yeah, so I should clarify. So sometimes solutions for this phase space density, we really work in phase space. So actually, in the context of globular clusters, there's a whole literature on what are called Fokker-Plonk approximations, where instead of following individual particles, you work basically for approximations of the Boltzmann equation, which I'm going to talk about in a bit. But it's still the case that for a lot of cosmological simulations, we're following particle trajectories, where the definition of particle is going to be interesting. But we still have a set of equations of motion typically that we're solving. Okay, so all right, so there's so that is one level of consideration. Do we just have a few particles, or do we have like a ton of them? And what I should say is actually globular clusters kind of live right here. They're in the sort of like 10 to the 6 particle range. But when you're in the huge number particle range, which is typical for dark matter applications, which given the title of the conference, I'm assuming is the thing that most of you care the most about. And next level consideration is whether when you're looking at the available states for your particles, if there's really low occupancy or if there's very high occupancy of those states. And if you have very low occupancy of states, it really makes sense to talk about dark matter or your other particles as particles. It's sort of when I teach statistical mechanics, I talk about, if you're a person in the state of like Wyoming or Montana, there aren't that many other people around. So it makes sense to talk about you as some distinct particle. But for other dark matter, candidates, like axions or axion-like particles, especially axion-like particles that have an extremely low mass, the occupancy is very high. And so it makes more sense to represent that dark matter candidate as a field or a wave rather than as a discrete set of particles. And so we're going to see that come up again probably in tomorrow's lecture. Okay, so that's one consideration of this axis, is basically how many particles do you have? And if you're in the high particle number limit, should you really be thinking of particles as particles, or should you really be thinking about fields instead? The other consideration that really matters for your approach to simulations is what the mean free path of scattering is compared to the size of the system. So here, lambda is the mean free path. And so if you have contact interactions, then you can think of the mean free path as basically the typical distance between scatters. Now for gravity is a long range force. And so when you're thinking about the mean free path for a long range force, it's not the distance between scatters that matters. In some sense, that doesn't even make a whole lot of sense to talk about, because like the moon is far away, but it's always sort of interacting with the Earth. So you could think about like, how would you quantify the interaction between the Earth and the moon, given this long range interaction? Instead, if you have long range interactions, whether it be gravity or in some of these self-interacting dark matter models that we'll talk about tomorrow, what it really means is the distance you have to travel for the momentum or energy of the particle to change of order unity. Okay, so that's typically what we mean by mean free path. The question is, how does that compare to the scale of the system? So in fluid dynamics, the way we quantify this is in terms of something called the Knudsen number, which is the mean free path over the characteristic size or scale of the system, which I'm calling L here. And we have these extreme limits that we are most often working in. So the two most common regimes that we work in are when the Knudsen number is very, very much less than 1. So when the mean free path is very, very small compared to the system size. Or if the other extremum is if the mean free path is gigantic compared to the typical system size. there are well-defined approaches to simulations in these limits. The case where it's really a pain to figure out the best approach is when the Knudsen number is about 1. Okay, and so to just give some examples, astrophysical gases are almost always in this very small Knudsen number limit. So if you think about like just Coulomb interactions in the gas, you know, those Coulomb interactions, like when you have like, you know, just some chunk of gas in space, or even the gas that you're breathing in your room, the mean free path is very small compared to the system size. Okay, so anytime you've got anything electromagnetic, you're typically in this low Knudsen number limit. So that's the regime where we start talking about fluids, where the fluid approximation becomes good. On the other hand, cold dark matter, so cold collisionless dark matter, we basically assume that the mean free path is effectively infinite, so that dark matter hardly ever at all interacts with it itself. In that case, we're in essentially the collisionless limit. Now, as I'll talk about a bit tomorrow, the tricky situation is when your Knudsen number is of order 1, which is the case for dark matter self-interactions. And so then you're neither in the sort of typical cold dark matter limit that a lot of simulations are pros at describing, or astrophysical gases, for which there's a whole body of techniques. All right, so this is sort of the space in which different approaches, you can quantify your different approaches to solving your initial condition to final condition problem. So we got basically how many particles do you have, and how often do they scatter? Okay, and then to sort of answer the question a little bit that came before, another thing to consider is basically whether you care really about precise solutions to your problem, or if it makes more sense to think about a statistical ensemble of possible solutions. So if you care about some near-Earth asteroid hitting the Earth, you really care about very exactly solving a set of initial conditions, right? You really want to know if that asteroid is going to hit Earth or not. On the other hand, for cosmological systems, we're often doing realizations of patches of possible universes. And there we care more about sort of the ensemble of solutions that you might get. Now, one tricky thing is that for even a lot of small n systems, and we're going to talk about this more in a bit today, is that because when you go beyond the two-body problem, systems are chaotic. You can often only figure out exact solutions as to, you know, whether the asteroid's going to hit you or not, only for a limited range of time, after which you really, even if you can give every object in your system a name, at some point the best you can still do is a probability distribution of outcomes rather than a perfect solution. And that may seem strange because, like, you know, if you have a conservative forces and some initial conditions like are not your final solutions, you know, completely deterministic. And the issue is that that may in theory be true, but when you're actually solving equations, there's always numerical error, and chaos means that you just you're really better off thinking about probability distributions of outcomes rather than a specific outcome. All right, and this thing that I label here is Miller's instability. That basically is a statement about chaos in large n systems, where n here is number of particles. When you got a lot of particles, your system is super chaotic. So there's that. Okay, and so let's talk about where familiar systems lie in this space. So planetary systems and multi-star systems tend to be in the small number of particles, but semi-scattery regime. Globular clusters, which are these very dense star clusters of still somewhat mysterious origin, they tend to inhabit this sort of 10 to the 6 particle range. We're not going to talk about globular clusters, but they're really fascinating. And especially if you're a dynamics nerd, I strongly encourage you to read more about globular clusters because they are super awesome. Okay, and then as I showed before, we've got various cosmological components. We got our cold dark matter, we've got self-interacting dark matter, and then we have astrophysical gases over in this large N limit, but with different Knudsen numbers. Okay. And so the outline for sort of the rest of today and tomorrow is that we're going to talk about few body systems first. And that's because I want to introduce different methods for integrating orbits that are going to become relevant when we get to the large N system. Then we're going to talk about these, what are called N-body problems, which is basically if you just had a universe of dark matter, how would you simulate that? And then we're going to add gas at the end and put everything together. All right, so that's sort of the outline for the rest of the today and tomorrow. So let me stop here and ask if there are any questions before we go on to talking about different types of problems and the approaches to solving those problems.
Yeah, questions? There are no questions in the room, and I don't see anything in the chat either. So you're good to go, Annika?
Okay, thanks. All right, and you may hear an occasional meow in here, and that's because I've got cats coming sort of in and out. I've got 4 cats, and so they are frequent call interrupters. Okay. All right, so let's move on. Okay, so we're going to talk about few body gravitational problems first. And again, that's because some of the techniques that we use to solve those problems are going to come up again when we talk about cosmological dark matter problems. Okay, so again, I'm going to switch to a couple of websites which are linked here. But basically the issue with, and the reason why we have to use computers to solve initial conditions problems is because gravity is mean. So, and what do I mean by that? Well, so it has been known for a super long time that the two-body problem, if you just have two essentially point masses or close to point masses, you get these beautiful solutions, these beautiful conic section solutions. So in this case, we've got a small object orbiting a large object, and you see that the orbit is this perfect ellipse. So this problem, this two-body problem, is completely analytically tractable, has been analytically tractable for centuries, and it's just beautiful. Now the problem is when you introduce even one more body in the system, is that the problem is that you literally get chaos. And what I mean by chaos is that if you have some set of initial conditions, and then in sort of a butterfly universe have an almost identical set of initial conditions, or you have a slightly different numerical method for solving your system, is that your final end product, or at some much later time, the systems look completely different from each other. So what I mean by chaos here is that if you start with almost identical initial conditions, you can get vastly different outcomes. right? So it's not like in perturbation theory where if you have a small perturbation to your problem, you end up getting a solution that is not so dissimilar from your, another perturbed problem. In this case, we get a very different outcome. And so one great way to see this is actually through this one Twitter bot, which sounds nuts, but here we go. So there is something called the random 3-body problem Twitter feed. And it's like amazing. So they start with different initial conditions here. Each of these colors represents a different object. And you can see how these systems evolve. And so they show what the initial conditions are in each case. They show you what the masses of the 3 bodies are, the velocities, the initial velocities, and the initial positions. And you just get these like very, not very ellipse looking solutions. Okay, and so when you add even one more body, like in these systems, you have to go to a computer to solve these, and you're often going to be talking again about looking at the probability distribution function of outcomes rather than a specific outcome. Now, what I should say is that there is an enormous literature just on the 3-body problem, not even adding extra bodies to the system, and even without GR. There's a huge literature. There are whole books written on the 3-body problem. It is a very active field of research. And so I have a whole bunch of links about 3-body problems. But basically, once you add that one more body, we're not talking about ellipses, beautiful, perfect ellipses, or hyperbolas, or parabolas as solutions. Instead, we're looking at systems that look like this. Okay, so, okay, I just lost. Oh man, okay. I gotta find my Zoom window again. The problem when you have PowerPoint going is that sometimes you just lose every other window behind it. Okay. All right. And so one very dramatic example of chaos in few body systems is considering the evolution of our own solar system. So our own solar system is a bit unique compared to extrasolar planet systems that we've observed, in that we have 8 planets on almost completely coplanar, almost completely circular orbits. In the past 20 years, thanks to missions like Kepler and TESS, we know that systems that look like ours are not especially common. And the question is our solar system going to continue to look the way it does? So, so there's this famous Nature paper by Lascar and Gastineau, where they take our solar system and evolve it 5 gigayears in time, and they are slightly varying the initial conditions of Mercury, and seeing what happens in this case to the orbital eccentricity of Mercury, which is the innermost planet in our solar system with time. Okay, and so so let's look at what is going on in this picture. So in the top panel, what we've got is just purely Newtonian gravity. There's no Earth's moon in here. And in this case, the initial position of Mercury is varied by only 3.8 centimeters. Okay. And look at all these different outcomes for the eccentricity of Mercury with time. I mean, its eccentricity now is, should have looked this up before, but it's about, 0.2 if you look at these initial conditions. Look how many different, and each of these colors represents a different individual simulation. And there are 200 simulations shown here. look at this huge variety of outcomes. And in this bottom model, they have their full solar system with GR and moons. And in this case, they've got 2,500 different initial conditions, where the only difference is that they've changed the semi-major axis of Mercury's orbit at the beginning by 0.38 millimeters. Okay, and still look at this huge variety of different outcomes. So basically, when the eccentricity goes to 1, what that means is that Mercury has just crashed into the sun. So goodbye, Mercury. And you can see in a fair number of these cases that Mercury crashes into the sun. Okay, so this is an example of numerical chaos. And one thing to note is that you could really only solve with relatively high confidence in the future, just a few tens of millions of years ahead. So if you want to know what our solar system is going to look like in 5 million or 5 gigayears, the best that we can really do is basically a statistical just probability distribution. Now, if you take much smaller time steps, and we're going to talk about that in a bit, you can maybe extend this a little bit more, but then you sort of run out of your computational time. So if you take very small time steps when you're trying to solve the equations of motion, you're just going to blow up your total CPU time. And so anyway, so there's some trade-off. But basically, like the main point here is that even for a relatively few body system, you can have very different outcomes depending on the initial conditions. And that is a sign of chaos. Okay, so let me talk. So that was like a planetary system application of a few body problem. Let me talk more about some fundamental physics applications, since I'm guessing most of you are fundamental physics people. So another example, and we're going to get to dark matter in a second, I promise, but another application is tests of GR. So one
Sorry,
way
there's a question here.
Oh, yes.
Hi, sorry to interrupt, thanks. On the previous slide, with simulations like this one, if we had, in theory, an infinite amount of computing power and we could take infinitely small time steps, would the outcomes of the system be, would we be able to predict them exactly, or would there still be this fluctuation?
Oh, that's a good question. So having smaller and smaller time steps basically just delays the onset of when you get this chaotic divergence. Yeah, but so yes, so if you have super tiny time steps, then you can delay it. But whenever you're dealing with a finite time step, you're still, that is going to induce some error. Yeah.
One more question.
Building on this time step thing, is there some sort of analysis that you can make to roughly tell you when you're going to bump into this chaotic regime? Because I mean, if you're right, I would need to set a scale, a step, right?
Yeah. So there is a whole literature on the subject, especially in sort of the planetary dynamics community. So some of the keywords that you'll be looking for are Lyapunov exponent. But if you pick up like a planetary dynamics paper or book, there will be a discussion of when the really chaotic solutions step in. So one book I would recommend is Murray and Dermot's Solar System Dynamics book. There's a really nice section on chaos in there. And if you look at Barbara Ryden's book on dynamics, which is linked in the references, she has a nice description of chaos in the asteroid belt. But yeah, so I would definitely recommend going into the planetary dynamics literature for more on that. So great questions. But it's also the case that sometimes things are just chaotic. So even if you start to things with very small separations, you will still fundamentally get chaotic orbits. And so in that case, it really becomes sort of an initial conditions problem. Like, how well do you know your initial conditions? So it's not just about time stepping and the accuracy of each solution, but it's fundamentally like the underlying nature of the system. Like in other words, it's not just the time stepping that matters, it's how accurately you know your initial conditions that matters as well. So in this case, you can see that even an uncertainty of 0.38 millimeters drives these very different solutions. Okay, so another application is, as I mentioned before, tests of general relativity. So this has become a hot topic in the last few years in the context of the LIGO and Virgo gravitational wave experiments, where we're looking for the mergers of binary black hole systems or black hole neutron star or neutron star systems. So one of the important things that you need to know about whether the number of black hole mergers you see is what you expect or not, and the properties of those mergers, is understanding a bit about the initial conditions. And so as it turns out, being able to model encounters between binary black holes and other objects that are nearby matters for figuring out the structure of the binaries before they merge and the frequency of the merger rate. So in this paper, they consider a series of weak encounters between just stars in a star cluster and a binary black hole system. And so these are basically a set of 3-body problems that they're solving for. And so what they show in this paper is that with a set of weak 3-body encounters, and by what I mean by weak is if you have a binary star system and then you have a pretty distant encounter of another star, if you have a series of those, then you can dramatically affect the in-spiral rate for LIGO and LISA. Okay, so these few body problems and solutions to them have become a hot topic in the studies of GR and also just the whole world of compact objects to determine basically what this type 1 supernova rate is as well. And so there's a lot of really excellent work in that context that is pretty recent. So I've linked a few papers here, and then I recommend checking out this YouTube page by Joe Antonini, who was a grad student at OSU, and he's got some really great videos of 3- and 4-body problems. Okay, now bringing things a bit closer to dark matter. So this is a graphic that illustrates some work from my own PhD thesis, where I considered dark matter capture to the solar system, either by a direct encounter of a dark matter particle with a solar nucleus to basically have that dark matter particle lose kinetic energy to solar nuclei and become bound to the solar system, or to experience gravitational 3-body encounters with the sun and honestly mostly Jupiter, where Jupiter slingshots dark matter into the solar system. Okay, and so if you want to understand the annihilation of dark matter in the sun, or the detailed velocity distribution of dark matter at the Earth for direct detection experiments, you have to include these effects of dark matter capture to the solar system. And so, or the gravitational focusing of dark matter in the solar system. So I link here a few papers about that, but that's sort of a set of dark matter 3-body problems that matter for the indirect detection of dark matter in the sun and the direct detection of dark matter at Earth. Okay, and the final application I want to talk about is the missing satellites problem. So the missing satellites problem, which I'm going to talk about more tomorrow, is what we call this issue where 20 years ago, if you looked at dark matter only simulations of Milky Way-like systems, so this is a snapshot from Ben Moore's classic paper where you have this Milky Way mass dark matter halo. Here the color contrast marks density. So white means high dark matter density, black means low dark matter density. If you looked at this Milky Way-like system, you'll notice that there are quite a lot of knots of dark matter inside this Milky Way mass system. Each of these little knots is a dark matter halo, a subhalo. And by that subhalo, what I mean is a small halo that orbits a larger halo. This Milky Way type system had many subhalos, but as we'll talk about more later today and tomorrow, galaxies live in halos. So if you took each of these little knots, these subhalos of dark matter, and assumed that a galaxy lived in them, then these simulations would predict far more galaxies than 20 years ago were observed around the Milky Way. So this is another representation of that from Anatoly Klipin's paper. So these papers came out at similar times and basically made the same observation. So in this case, Anatoly Klipin quantifies the number of halos in terms of like the peak of the circular velocity function in each halo. So basically, if you put particles on a series of circular orbits, what is the highest speed circular orbit that a particle would have in a halo? And the observations of the Milky Way and Andromeda were these sort of triangles 20 years ago. And the predictions for what you should see in terms of the number of satellites of the Milky Way and Andromeda is more in this red. Okay, so this mismatch was called the missing satellites problem. I have a lot more to say about this later. But one of the issues with this problem, there's sort of a couple of issues. One is that the Milky Way has the Magellanic Clouds, which I'm going to talk about much more today and tomorrow. And the Magellanic Clouds in dark matter mass are about 10 to 20% of the Milky Way's mass. So the Magellanic Clouds are major perturbers to the system and also can contribute satellites. So if you fully want to understand the Milky Way's satellite population and ask questions about, whether the number of satellites is what you expect or not, or whether you can explain a lot of effects with tides, for example, you really need to understand how the satellites of the Milky Way and the Magellanic Clouds, what their origin is, and then what their orbits are in that system. And so this is a set of plots that I took from a paper by Aug3 Patel. Aug3 is a Miller Fellow at Berkeley now. But what she's showing here is basically the orbital evolution of the Draco dwarf galaxy, assuming different sort of mass models of the Milky Way and Magellanic Cloud system. And in this case, she's taking initial conditions or really rather final conditions. So time of 0 means today, and this is look back time. So this is like 6 gigayears ago in the past. She's taking the position and velocity coordinates that we measure today. In this panel taken from a paper by Tony Sohn, and in this case from a paper by Amina Helmi, that was sort of the first Gaia data release paper. And she's basically showing what the orbits of the Draco dwarf galaxy look like for different mass models of the Milky Way. Here, blue and orange represent 2 different halo masses of the Milky Way. And then the different line styles denote whether you've only included the Milky Way's mass model, you've included the Large Magellanic Cloud, and in the case of the dotted, if you've included all the major perturbers in the Milky Way system. And so what you find here is, depending on your mass model of the Milky Way and Magellanic Cloud system, is that the orbits look quite different. And so our interpretation of the Milky Way satellites depends on our understanding of their orbits. And as you can see here, the orbits look pretty different in look back time, given a fixed set of initial conditions, depending on your mass model and also actually how accurate your initial conditions are. So you can see that for these 2 sets of initial conditions, you can see that there are actually some significant variations, especially in this, this second Milky Way mass model that includes both the Milky Way as well as the 2 clouds.
Question here?
Thanks. On the right plot, are those dotted orange lines showing us that one of these is going to escape our gravitational potential?
So what this shows is that Draco, in this case, that Draco fell in to the Milky Way 6 gigayears ago. So the fact that these lines here are sort of less than about 150 kiloparsecs 6 gigayears ago, that's a sign that Draco was already bound to the Milky Way. And this line here shows that basically it sort of fell in and became part of the Milky Way, more recently than 6 gigayears ago. Yeah, but that's a great question. Yeah, so this is look back time. So this is actually earlier, like farther ago in the past is a bigger number, and 0 means today. Just a bit confusing. Okay, and so so another example of this is when people are trying to, this is a very busy plot, when people are trying to figure out the pericenters of Milky Way satellite orbits. And the reason this is important is that you want to know whether the Milky Way satellites are heavily tidally stripped or not. It has a lot of implications for whether our satellite population is typical or not. But to figure out if those galaxies, like what their pericenters are, you need to know what are the positions and velocities of those satellites today. And then when you integrate those orbits in a Milky Way mass model, where's the pericenter? So this is a snapshot I took from a paper by Josh Simon, who looked at orbits of a bunch of Milky Way satellites using Joe Bovey's GalPi tool. And one of the exercises for Thursday that you can choose from is actually learning how to use GalPi. But here in sort of XY space, XZ, and YZ space, Josh is showing the orbits based on Gaia DR2 proper motions of these satellites. Okay, so that was a long preamble on examples of few body problems, some of which have dark matter applications, some of which are just cool, so I wanted to show you. And so the question is, like, how do you actually, what went into those orbits that I showed you, or figuring out those solutions? And it seems like simple enough, like, you just have some equations of motion, you have a set of coupled ODEs. What's so hard about that? So let me tell you why, what sort of things need to be on your radar when you're thinking about solving these few body problems. Okay, and so I'm gonna just show an example here. So in each of these panels, I'm showing an orbit with a different eccentricity. So in all these cases, I've chosen basically to have an Earth going around a sun, but where I've changed the eccentricity of the Earth's orbit. So in this case, the eccentricity is 0.9, here it's 0.99, and here it's 0.999. Okay. And I forget exactly how long I ran these simulations for. Oh, I guess here we go. 10,000 years. So this was a set of simulations I ran for my the first talk I gave on my thesis work when I was in grad school. All right, and so you know, because these are two-body problems, that the analytic solution is just an ellipse. So if I ran this 10,000 years, you should still just see a perfect ellipse. Now, the thing is that you don't see a perfect ellipse, right? So you see this sort of like what looks like kind of an in spiral. You can quantify this in terms of energy. So what I'm showing on this plot here is the energy of the system E at some time compared to the initial energy EI over that initial energy. So it's basically how far is my energy off from my initial energy? And I know analytically that energy is conserved. So really all these lines, if I had solved this perfectly numerically, all these lines would be at, below this lower axis of this plot. And instead what you see is that the energy errors grow in time. So the worst case is this extremely high eccentricity orbit at 0.999, where I'm getting like factor of like, 100 to 1,000 fluctuations in the energy. Okay, and so these are, this I solved with just a Runge-Kutta integrator, which is maybe something that you've used. And so this is real bad. Like we do not want to have these trending energy errors, right? Like we know just by eye that this is not great. Okay, and what that means is that when you're looking at these few body problems, and again, what we're going to see when we come to cosmological simulations, is that you need a different approach to integrating orbits. Like you really don't want to have those growing energy errors. That is real bad. And so instead, what people do is they go to a class of integrators called geometric integrators. And what that means is that for these integrators, they explicitly conserve some geometric property of the differential equations. So there are different classes of geometric integrators. There are ones that are explicitly energy conserving, some that are time reversible, and some that are symplectic. So I've got some spare slides at the end of this on symplectic integration. But basically, in this case, each time step that you do in the integration is a canonical transformation. So if you're a Hamiltonian mechanics nerd, you can super nerd out over symplectic integration. And so I've got some notes on that. Also, sometimes you have to make a change of variables to make the solution more practical. And again, the planetary dynamics community and the globular cluster community have done a lot of work on clever ways to make your equations behave better numerically. So I'm just going to show you. Oh.
Thanks. Yeah, so for that first bullet point, just the general idea of this geometric integration, I don't think I quite understand what you mean by the methods preserving the geometric properties of differential equations.
Okay, that is a great question. So by this, what I mean is that you want to preserve some symmetry or some conservation law in the integration. So one is like, for example, time reversibility. So if you want to start with a set of initial conditions and integrate forward in time, if you then go backwards in time, you should get back to your initial condition modulo a little bit of like what's basically oscillatory numerical error. So instead of having, where that energy error before here goes off a cliff, if you have an oscillatory error, then you can generally go from your end state to a backwards integration and end up basically at your initial conditions. And where the equations that you use are time reversible. So in the Runge-Kutta integration, if you start at your final step and work backwards, you end up with a set of equations that looks different than if you started at the beginning and then took a step forward in time. So the forward and backward equations are not time symmetric.
Yeah, go ahead.
Actually, that answered my question. Thank you.
Okay, so I'm just going to open a door to let a cat out. There we go. Okay, so instead, as I said before, people use these geometric integrators. So one very, very popular choice is this thing called a leapfrog integrator. So this is what's called a second order algorithm. So there's like if the time step is h, there's sort of like h squared errors of order h squared. And so the set of equations that you use looks like this, where again, q and p are the configuration and momentum space coordinates. And this u is a potential. Like if this were a gravitational problem, this would be the gravitational potential in the problem. Okay, and so this is the algorithm that you go from a step at t equals 0 to a time step that's t0 plus h. And so what I should say is that this is the workhorse of cosmological simulation codes. So if you look under the hood at like one of the gadget codes or any other cosmological code, under the hood for integrating trajectories is the leapfrog. And so let's talk about how this works. So in this case too, I've got the simple Kepler two-body problem. And initially, it does not look necessarily super amazing here in the sense that I have these different eccentricities again, and they clearly are not perfect ellipses. But what you can see if you look at this evolution of the energy errors with time, is that the energy errors are oscillatory. Okay, so you're not seeing the energy going off a cliff, but for each one of these different eccentricities, you're seeing these oscillatory errors. And so what that means is that, in the case of this eccentricity, we get some precession of the orbit, but the overall shape of the orbit is still an ellipse. It just is an ellipse that precesses. And so if you care about a statistical ensemble of solutions, then having these precession errors is vastly preferable to having energy errors where you get artificial inspirals. And you can control these precession errors by either going to a higher order integration scheme. So that's one option, or by taking smaller time steps, or in the case of my own PhD thesis, I actually went into a time transformed coordinate system where I was much better able to control the precession errors. So there are steps that you can take to do even better, but at least for this set of solutions, we're not seeing basically, our energies like completely blow up. We get these oscillatory errors, but then, we have a different issue that we need to deal with. So being able to conserve energy is really important. And so this sort of leapfrog does better on this. And again, you can control some of the errors here in part by just making your time step a little smaller. Okay, so one example of a higher order accuracy system or simulation tool is this IES 15 code, which is the sort of under the hood integration algorithm that goes on in Hanno Rein's basically debris disk simulation code package. But this is a 15th order integrator. And if you're interested in what that really means, I would recommend taking a look at this paper on that. Okay, but these geometric integrators, and especially this simple, very simple leapfrog algorithm, are what is under the hood of all these simulation softwares. Okay, one caveat though is that really what happens in a lot of cosmological codes is that you have different time steps for different particles, which actually violate some of the time reversible and symplectic properties of the leapfrog integrator. So if you want to learn more about that and how people try to cope with that, I recommend looking at Fokash Pungo's 2005 paper where he describes the Gadget2 simulation code. This paper is what I would say, it's a good description of what is inside the Gadget2 simulation code. Gadget2 is the predecessor of today's modern Gadget4 code that you can download and run yourself. It's sort of his newest tree SPH, and those words will make more sense later this week. It's his newest public iteration of this code, but a lot of the guts were described in Gadget2. And what makes this paper great and stand the test of time is that it's a lot about algorithms and how to think about problems, not just about the Gadget2 code, but more generally what you need to be thinking about when you're writing or running a large cosmological simulation code. Okay. So if this sounds interesting to you, there are some things that you should know or know how to do. So one thing that you should try to do if you're really interested in this field is that you should write your own leapfrog integrator. And I'm going to put an exercise in the Google Drive, which is one of the problems that I give to my grad dynamics students at OSU. It's basically a simulation of a Tatooine-like system. So if you're not a Star Wars nerd, just Google Tatooine and you'll see what I mean. But that's something that you should definitely do, is write your own leapfrog integrator and integrate some system that you think is interesting. Another thing, which if you're interested in this field, you should learn how to do, is figure out how to test for convergence in solutions. Like, how do you know that your integrator is working as well as you want it to do? Another is to learn more about geometric integration more generally. And so I have a bunch of references in my notes about that. And then finally, if you're interested in things like orbits of satellites in the Milky Way, or the orbits of stars and galaxies, then you should really learn how to use Joe Bovie's GalPy Python package. If you're interested, especially in tidal streams, I would recommend checking Adrian Price-Whelan's Gala code. So those are all things that are good to try and learn more about. Okay, so this is maybe a good point for me to ask if there are more questions before we spend just a few minutes on cosmological stuff.
No, nothing here in the room, and neither on Zoom.
Okay.
Yeah, one question here. Yeah.
So you talk about initial conditions. But what about the boundary conditions that we use in these simulations? It depends on the method you are using.
Sorry, was it something about initial conditions? I couldn't really hear very well what the question was.
It's about the boundary conditions.
Boundary conditions?
About the boundary conditions, actually.
Okay, that is a great question. So that is going to be something that comes up more in cosmological simulations than in these few body problems. Few body problems tend to be initial value problems, but for like GR, even with binaries, even for GR and for cosmological codes, boundary conditions do matter. And at least for cosmological problems, you usually have, okay, now I'm forgetting the word, but sorry, I'm just totally blanking, but you basically connect one side of your box to the other. So you have, so you don't have like a hard, but you have like a, sorry, I am just losing my words today. Periodic. Thank you.
Periodic, yes.
Yes, thank you. Okay. All right, so I just want to set up a little bit on cosmic structure and then we'll do the deep dive tomorrow. Okay, so I'm going to talk first about n-body problems. So n-body problems are really problems where you have an almost collisionless or collisionless system. And then hydrodynamics problem is when you're in that limit where the mean free path is super tiny. But really to describe cosmology, you need both. Like, because galaxies are basically big balls of gas and really dense patches of gas that we call stars. So galaxies are really hydrodynamic, but then dark matter is really an n-body problem. And so to describe the universe together, you need both. So I'm going to talk about them together, and then we're going to talk about n-body and then about hydro. Okay, so why do we care? So this is an image from NASA where we're showing the evolution of the universe in time. And so this outer scale sort of denotes the expansion history. So where this is more fluted or the slope is steep, that's accelerated expansion. This is early times, late times. And so what's important in cosmology is that dark matter governs the dark matter governs the expansion history of the universe. It really dominates from sort of near-ish the CMB era to right around the middle age of the universe when dark energy takes it away. But really dark matter explains the expansion history of the universe, or is responsible for the expansion history of the universe, but it also governs the growth of structure. Okay, so without dark matter, you don't really form galaxies. And so thanks to dark matter, we have these overdensities, matter overdensities that collapse, form halos, and then dark matter forms in them. So this is a little cupcake I use to represent the role of dark matter in the universe. So one thing is that each component of this cupcake represents a different part of the universe. The cake part is dark energy. The frosting here is dark matter, and these sprinkles are, baryons, gas, dust, and us. And dark matter basically holds the baryons together, which is why I love the analogy of dark matter as frosting. It sort of holds the baryons together. And so if I look at this in a more quantitative way, this is a simulation by Farkas Springer that's part of the Aquarius series. And this purple thing is a dark matter halo, and then a galaxy lives inside of it. So basically every time you see a galaxy, what that's telling you is that there's a dark matter halo that galaxy is sitting in. And that dark matter halo is keeping that galaxy together. Okay, and so we use galaxies to trace the dark matter on large scales. We use it to trace the clustering of matter. And this is another great slide from one of Fokash Pingo's talks, where he shows galaxy surveys, in this case, the CFA Great Wall observation from like the 80s, the Sloan Great Wall from like the 2000s, and then the 2-degree field survey here. And then he's showing simulations of dark matter halos from the Millennium simulation, which I'll talk a little bit more about tomorrow. And so these simulations show where the big halos live. And you can see that the clustering of halos looks an awful lot like the clustering of galaxies observed in these 3 different galaxy redshift surveys. Okay, and so dark matter forms like the backbone for structure formation. Now, the other thing that is important is that you can actually use the clustering and the number of halos to constrain something about dark matter. So these simulations here are just with cold dark matter, which I'll talk about more. So your plain vanilla, non-collisional, totally stable dark matter forms the backbone of these simulations. But you can also use the abundance of those halos to learn something about dark matter. So what I'm showing in this plot is how you could possibly constrain how stable dark matter is or not. On the x-axis, we've got halo mass. The y-axis, we've got the number density of halos. And each panel represents a different redshift. Now, each of these lines, the colored lines, represents a slightly different cosmology, assuming cold dark matter. So it's basically, at the time I wrote this paper, these would be WMAP cosmologies in color. And then this black line shows the abundance of halos as a function of mass for a decaying dark matter cosmology. So assuming that dark matter is unstable instead of stable. And so what you can see by looking at where this black line is with respect to these colored lines is that the evolution of this halo, what's called mass function, looks different for decaying dark matter cosmologies than for cold dark matter cosmologies. So in principle, you could use the abundance of halos at different redshifts to constrain the stability of dark matter. And again, the way you would reveal that is by looking for galaxies. Okay, something that you may care more about is dark matter in small scales, because small scales is typically when we talk about dark matter and fun dark matter phenomenology, that's on scales that are small, that are subgalactic. So, and by what I mean by subgalactic is something that's smaller than the Milky Way. Okay, and so I may actually stop here for today. So tomorrow I'm going to pick up on talking about dark matter on small scales, and then really getting into the nuts and bolts of simulations. Let me ask if there are any final questions for today, because we're coming up against 5 o'clock your guys' time.
Yes, one question here.
Okay.
Yes, so you were mentioning at the beginning the connection between the missing satellite problem and our interpretation of the orbits. I didn't quite get this part. Could you mind explaining it again, please?
Yeah, that's a great question. So one of the issues with these, so there are several connections. One is whether some of these satellites could come in with the Large Magellanic Cloud or not. And the issue is 20 years ago, people didn't really have Magellanic Clouds in their simulations. Intriguingly, it's been shown recently by Ethan Nodler that to explain the population of Milky Way satellites in the dark energy survey, you have to include the contribution from the Magellanic Clouds, which means you have to understand the dynamical history of the Magellanic Clouds and the satellites it brings in. The other issue is sort of a subtle issue of whether the satellites that we see are heavily tidally stripped or not. And the issue for that is sort of a subtle question about what we consider to be really tidally stripped in a simulation versus observation. So it has to do with the definition of when we consider in simulation a system to be still bound versus a galaxy to be destroyed in simulation versus how that works in observation. And so that is it's a subtle question that I think is still not totally answered by the community, but to understand how much a galaxy may have been tidally stripped and therefore whether you would have counted it in your simulation based prediction or not depends on the orbit history and the tidal stripping history of the object. Okay, and I see a question.
There's a question on Zoom. Yash, can you unmute and ask your question if you want?
Yeah, sure. So just, I mean, this might be a stupid question, but I mean, I was just curious, like, so you earlier talked about the dark matter captured in solar system. I mean, so does that affect, you know, I mean, are there any observational perturbations be in orbits of the planet, or I mean, are there any simulations that, you know, maybe capture this effect?
Yeah, that's a great question. So the total amount of dark matter that's bound to the solar system is at best the mass of an asteroid, like a typical asteroid in the asteroid belt. And that's sort of within 50 AU, so sort of the typical orbit of Pluto, which is, you know, a dwarf planet. So it's not much. In principle, like, we know how chaotic the solar system is, so in principle it should affect things, but quantitatively in terms of figuring out how much of an effect it has, at that point you really need to be simulating each asteroid in the asteroid belt, or not each asteroid, but above some comparable threshold. And so effectively the answer is that, you know, it doesn't really change things that, you know, enough. I mean, there are other perturbers that are important to get right before you consider dark matter. But that's a great question.
Okay, so if there are no further questions here or on Zoom, thank you very much, Annika, and we'll see you tomorrow.
Okay.
Let's clap for her.
Okay, so tomorrow, as I promised, we will really get into simulation codes and public simulations.